Welcome to the Deep Dive. We're the show that takes complex research, interesting articles, and our own thinking and boils it all down into what you really need to know.
That's the goal. Keep you ahead of the curve.
Exactly. So today, we're jumping into large language models. LLMs, we all see the amazing things they do, right? Generating text, handling information.
Absolutely incredible stuff. Poetry, code, summaries.
But there's always been this sort of nagging issue when it comes to really complex multi-step thinking like intricate planning or deep reasoning. They kind of stumble.
They do. It's like they're brilliant conversationalists, but get lost in a maze. They take one step, then another, very methodically, but maybe not always efficiently.
Yeah, that maze analogy is good. And for a while, the fix or partial fix was this chain of thought idea.
Right, Koti?
Which basically just means getting the LLM to think aloud, show its work, generate those intermediate steps before the final answer.
It's like writing down your calculations in a math problem.
Exactly. And it definitely helped, made them better at logic tasks, more robust. It did. But even with Coty, as the problems get bigger, more complex, they still hit a wall, don't they?
They can, yeah, because it's still fundamentally sequential.
Yeah.
Step by step by step. And if there are tons of possible steps, it can get computationally explosive. Still, like being blindfolded in that maze, maybe just talking about each step.
Okay, so what if? What if they didn't have to think just aloud, but could think, I don't know, in parallel? What if they could somehow see multiple paths at the same time?
Now you're getting to the heart of it.
That's what we're diving into today, right? This new approach. It's called chain of continuous thought, or coconut.
Coconut, yeah.
Yeah.
That's the acronym. And it seems to give LLMs this, well, the source calls it a superpower for reasoning.
A superpower. Okay. So our mission today is to unpack that. Why is this continuous thing so much better? What are these superposition states they talk about?
Exactly. And how could this change how LLMs handle really tough problems? Like navigating complex networks, which is the core example used in the research we looked at.
It sounds like a pretty fundamental shift.
It really could be. Less incremental improvement, more. A different way of thinking for the AI.
Okay, let's dig in. When we say sophisticated reasoning where current models struggle, what are we talking about? The source material uses this specific problem, directed graph reachability. Sounds a bit technical.
It does, but the concept is actually pretty intuitive. Think of any network, like a social network, the internet, maybe a subway map.
Okay.
These are graphs, points, or nodes. That's your stations, your websites. And connections, or edges, the subway lines, the hyperlinks.
Got it.
And directed just means the connections only go one way, like one-way streets.
Right.
So directed graph reachability is just a simple question. In this network, can you find a path from a starting node, say station A, to a destination node, station Z, following the one-way connections?
Seems straightforward enough. Why is that the big challenge?
Well, simple to state, but it's surprisingly fundamental. A lot of really hard problems in computer science, even theoretical ones like the Turing machine halting problem.
Oh, okay. That's a deep cut.
Yeah. But also practical things like making sense of huge knowledge graphs. They can all be boiled down, essentially, to variations of this reachability question. If you can solve this efficiently, you can solve a lot.
I see. So it's like a building block for more complex reasoning.
Precisely. It's a core test of logical navigation.
And how do current methods, like that discrete chain of thought, handle this? You said inefficiently.
Yeah, that's putting it mildly. The source points out it takes, well, in technical terms, ON2 decoding steps. N is the number of nodes or stations in your graph.
ON2. Remind me what that means in practical terms.
It means the work involved grows really fast, quadratically. If you double the number of stations, the computation needed could quadruple. If you have 100 nodes.
You could be looking at 10,000 steps.
Potentially, yeah. Or something in that ballpark. It just doesn't scale well. It gets incredibly slow and resource hungry for the LLM, which really limits the size and complexity of the networks it can handle.
Okay, so that's the problem. Slow sequential gets bogged down. So Coconut comes along with its continuous latent thoughts. What's the magic here? What makes it so different?
This is the really cool part. It uses this idea of superposition states.
Superposition. Okay, sounds like quantum physics. Are we talking quantum computing here?
Good question. No, not physical quantum mechanics. It borrows the term and the concept. Think of it mathematically. You know how in quantum mechanics a particle can be in multiple states at once until you measure it?
Sort of, yeah. The cat is both alive and dead.
Kind of like that, but for thoughts. Instead of the LLM picking one specific path, one discrete thought, like, okay, I'll try going from A to B, the continuous thought vector, this internal representation, It actually encodes multiple possibilities, multiple search frontiers at the same time.
Multiple frontiers. So it's like looking down several corridors at once.
Exactly.
Yeah.
It's very much like doing a parallel breadth first search, a BFS, but all within a single computational step of the model.
Okay, let me see if I get this. Traditional Kokanti is like, you're at a junction in the maze, you pick one door, go through, see what's there. That's a collapse state, right? You committed.
Yep, collapsed. You made a choice.
And you might hit a dead end, have to backtrack. Takes ages. But Coconut, with superposition, it's like you can simultaneously peek through all the doors leading out from where you are all at once.
You've absolutely nailed it. That's the core idea. Instead of the LLM's internal state saying, I am currently considering node B, it might represent something like nodes A, B, and potentially D are all currently reachable within my search. It holds that whole frontier of possibilities,
Wow.
all within one continuous vector. It explores many paths in parallel, which you can imagine is way, way more efficient.
The efficiency gain seems obvious when you put it like that, and the theory backs this up pretty dramatically, doesn't it?
It really does. The research shows something quite startling. A simple two-layer transformer model.
Just 2 layers, not these giant 100-layer models.
Just 2. Using Coconut, it can solve this directed graph reachability problem in D steps, where D is the graph's diameter.
The diameter, meaning like the longest, shortest path across the whole network.
Exactly. The maximum number of steps you'd ever need to take in the most efficient route between any 2 points. And crucially, D is pretty much always much smaller than N, the total number of nodes, often way smaller.
So instead of potentially n squared steps,
You're looking at D steps, which could be, say, log N or even less in some graphs. It's a massive theoretical improvement, exponentially better scaling.
that's huge.
And importantly, they show this works with standard positional encodings that LMs already use, like sinusoidal or ropey.
Ropey, right. Rotary position embedding. That's key for understanding sequence order.
It is. So this isn't some theoretical construct that needs a whole new architecture. It plugs into how LLMs already work. It's practical.
Incredible. Okay, so how? How does a 2-layer transformer do this? How does this superposition, this parallel search, actually happen inside the model? It still feels a bit like magic that it learns this.
It's elegant, actually. The theory breaks it down into what each of the 2 layers learns to do. Layer 1 becomes what they call an attention chooser.
Attention chooser.
Its job is basically smart copying. So if you have a token representing an edge, say the connection from node X to node Y, Layer 1 learns to use attention to copy the information about node X and node Y onto that edge token. It's like labeling the subway line token with the names of the stations it connects.
Okay, so layer 1 gathers and tags the relevant info for each connection. Makes sense. What about layer 2? That must be where the parallel expansion happens.
Exactly right. Layer 2 is where the node expansion occurs, the model's continuous thought state at that step. It attends or focuses on all the outgoing edge tokens from all the nodes that are currently considered reachable in its superposition state.
All of them at once.
All at once. So if its internal state says A and B are reachable, Layer 2 looks at all edges leaving A and all edges leaving B simultaneously. It effectively expands the set of known reachable nodes in one go.
And then those MLP layers, the processing units.
Yeah, the MLPs then kind of refine this. They filter out noise, maybe equalize the importance or weight of all the nodes that are now part of this newly expanded frontier. So you get a clean representation of the next set of reachable nodes.
What strikes me most about this is, you mentioned it learns this. The model isn't explicitly programmed. Step 1, copy nodes. Step 2, expand frontier.
Yeah.
This ability, this superpositional thinking, it emerges.
That's one of the most fascinating findings, yes. It emerges automatically during the training process. They don't directly supervise it to do a parallel search step by step.
Wow.
The model, through learning to predict reachability, figures out that this parallel superpositional representation is the most efficient way to do it. It discovers this strategy.
That says something profound about the learning capabilities here, doesn't it? It's not just pattern matching, it's finding efficient algorithms.
Absolutely. It implies an inherent ability within these transformer architectures to develop sophisticated computational strategies when given the right kind of problems and learning signals. It's less about hand-coding logic and more about enabling these emergent capabilities.
Okay, theory is great, emergent properties are fascinating, but does it actually work? Did the experiments back this up? Did the 2-layer model really beat the bigger ones?
Unequivocally, yes. The experiments align beautifully with the theory. They tested it on graph reasoning tasks, specifically using a dataset called PROSQA.
PROSQA, okay.
And the 2-layer transformer using Coconut. It achieved near-perfect accuracy. Really impressive.
Near perfect. And how did the traditional approach do A bigger model, say.
That's the kicker. They compared it to a much larger 12-layer model using standard discrete chain of thought. That bigger model only got around 75% to 83% accuracy on the same tasks.
So a smaller, simpler model using this continuous thought approach drastically outperformed a much larger, more complex model using the old method. So,
Exactly. Better accuracy with potentially much less compute. It's a very strong empirical validation.
and they could actually see this happening inside with visualizations.
They could. By looking at the attention patterns where the model focuses its computation, they saw clear evidence. Layer 1 was doing that copying task, putting node info onto edges, and Layer 2's attention was sharply focused on the outgoing edges from the currently reachable nodes, spreading out like a wave. It visually confirmed the parallel node expansion. They even saw it prioritize the frontier nodes, the ones at the edge of the search, just like a good BFS algorithm would.
Which ties into that other cool finding about exploration priority, even when they didn't explicitly train it to be optimal.
Right. Even with just random supervision on which nodes were on the frontier, basically telling it these nodes are reachable without saying how to search best. The model still learned to prioritize those frontier nodes and showed a bias towards optimal shorter paths.
So it naturally leans towards an efficient breadth-first search strategy.
It seems to, yeah.
Yep.
It implicitly learns to explore outwards systematically before locking onto a solution path. It suggests a really adaptive and, well, inherently efficient learning process is going on. It doesn't just find a solution, it finds a good way to find the solution.
Okay, let's bring this home. What does this all mean for you, listening to this? Why is this coconut idea, the superpositional thinking in LLMs, important?
Well, fundamentally, it points towards faster, much more reliable reasoning in AI.
Faster and more robust.
Imagine LLMs tackling problems that were just too complex or took too long before. Things like complex logistics planning, maybe discovering new scientific hypotheses by exploring vast connection spaces, or even understanding intricate legal arguments.
Stuff that needs many steps of logical connection.
Exactly. Problems where getting lost down one path could derail the whole process. This parallel approach makes them less likely to get stuck and much faster at exploring the possibilities. It's a real step towards AI that can handle more sophisticated planning and reasoning tasks.
So for you, it means the potential for AI assistants that are genuinely better at problem solving, not just retrieving information. More capable AI across the board.
That's the promise. It's a glimpse into how AI might evolve to tackle challenges that require deeper, more structured thought. Knowing about this puts you right at the cutting edge of understanding these capabilities.
All right, so to quickly recap our deep dive, we've seen that traditional chain of thought, while helpful, struggles with scaling complex reasoning tasks because it's sequential.
Right, step by step.
But this new approach, Coconut, uses continuous thoughts to achieve a kind of superposition, allowing the LLM to explore multiple reasoning paths in parallel.
Like a breadth-first search happening inside the model's mind.
And this enables even a simple two-layer model to drastically outperform larger models on tough graph problems, achieving near-perfect accuracy. And remarkably, this parallel thinking capability emerges naturally during training.
It's a fundamental shift from sequential processing to something much more concurrent and powerful for certain kinds of logic.
So here's the provocative thought to leave you with. We've seen LLMs learn to think in parallel for graph reachability, a core logical problem. If they can master this kind of superpositional reasoning here, what other complex, seemingly intractable problems could they learn to tackle this way in the future?
Think about scientific discovery, complex system design, maybe even forms of creativity that involve exploring many possibilities at once. How does our relationship with AI change if it can reason about complex choices, not one step at a time, but by holding countless possibilities in mind simultaneously?
How might this truly parallel thinking change how we use AI to solve the world's biggest challenges? Something to chew on.
Definitely food for thought. It opens up a fascinating new perspective on the future of machine intelligence.
Thanks for joining us on this deep dive. We'll see you next time.